So does anybody have any ideas on how we start this question? Prove the conservation of energy using Newton's second law. Anyone at all? Yep. We start by writing what the second law is. So F equals ma. We don't actually, in this case, we don't actually need to write down the fact that they're vectors, because we're going to be doing some mathematics in order to rewrite how this expression looks. But yeah, we'll start with F equals ma. What do we know that force does? When you exert a force on something, what are you doing to that something? What's the goal to exert a force on something? Sorry? Moving an object. When you move an object, what else are you doing? Work. You're doing, sorry? Yeah, someone said something else. Yeah. So you exert a force on an object, you are performing useful work on said object, right? So, should do a different color. So, exerting a force, a resultant force, exerting a force on an object always results in work. Okay? So if exerting a force on an object always results in work, and we know that work done equals force times distance, how might we rewrite this expression? Yeah. So you would basically do work done equals force times distance and rearrange it to make force the subject, right? So I'm having a bad pen day. Like, I can't understand why these pens are so bad. So we know that work done equals force times distance. So force is effectively work done over distance. Now, it's not going to stay like this, because there's another way I want to write this. So, work done over distance equals ma. I want to have a closer look at this work done over distance, and I want you to imagine, the easiest way to imagine work done over a certain distance is to imagine that you're raising an object a certain height. You can do work done. In fact, you don't need to like restrict it to that. Imagine squeezing a spring. You studied springs, right? What happens when you stretch out a spring or you squash it?
It changes length.
It changes length, so there's an extension, right? And when you squash it or you stretch it out, what do you feel acting against you? Tension, force, you know, whatever that sorry? Yeah, there's another term for it. Restoration force. Whatever the restoration force is in that spring when you squash it or you stretch it out is what you would feel. The reason why you feel a restoration force is because when you squash a spring or you stretch it out, you are doing useful work on that spring. You are building potential energy in that spring. The same thing as when you raise an object a certain height. You are building potential energy in that object because you are doing useful work on it, right? I can literally just call this work done potential energy. In fact, pretty much all work done on any object or in any situation results in potential energy. Okay? It could be some chemical reaction as well. Could be something physical. Could be nuclear. Okay? Anytime a force is exerted on an object or in a situation, work is done to build potential energy in whatever that thing is. And that's what results in action at the end of the day. So if I'm, okay, I have this habit of talking too much and running away with myself. Work done is basically potential energy. Okay, so I'm going to rub that out, and I'm going to rewrite it as PE over X. I'm not done though. I'm not done because the force may change. Okay? You're not always going to be exerting a constant force on an object. Okay? That force may change. That means I'm going to have a change in what? I'm going to have a change in potential energy over a change in distance. And, you know, that is what force eventually is. The same thing with acceleration. We can rewrite acceleration in a particular way. So, about 20 minutes ago, we went through some different ways to write velocity and acceleration. In this case, how would we write acceleration? d2x over dt squared. Cool. We have energy, we have force equals force, except that we've rewritten them mathematically different. Okay? Now, what does power equal? Energy over time. What else does power equal to? Force times velocity. Okay? So there's a reason why I wrote down that expression. Power equals force times velocity. Now we know that velocity, so if I write down here, P equals FV. Basically, what I'm going to do now is that I'm going to, in order to get a power on both sides, okay, because eventually I'm going to want to have my energy conservation expression just in terms of energy. The best way to do that is to get to power, right? Power is simply energy divided by time. And then at the end, I can just integrate. You've done integration, right? I know some of you haven't done it because you don't do maths. Put your hand up if you've done integration. Okay, most of you, but most of you don't do maths. How did you do integration?
Most of us do math. Yeah, most of us do.
Oh, it's only 2 people. Okay, cool. Integration is just the opposite of differentiation. If you don't know what differentiation is what enables us to do stuff like this. Yeah. Integration is the opposite of it. Eventually, we're going to get power, and we're going to integrate it with respect to time. Okay? So if power equals force times velocity, and I've got 2 forces here, I can multiply both sides by dx over dt, because velocity equals dx over dt. So what I've got in green here, or orange, is basically our toolbox. We just pick stuff from here and we dump it over here in order to use it, right? So we've got dpe over dx multiplied by dx over dt for velocity. And there's one thing I missed out, and that is the fact that this thing here is actually negative. Why do you think that is? If you've all studied a bit of Hooke's law, or you've looked at, have you ever seen the gravitational equation? The gravitational force equation? No? Okay, so that's A2 then. And you haven't done electromagnetism either. You've only done materials. What do you think that negative sign means? Sorry? It's not traveling in the same direction. Yeah. Rather, it's traveling in the opposite direction, right? So if you notice that the Hooke's law equation is F equals negative kx, right? F is the force exerted on the spring or string. K is the spring constant, right? You remember this? And x is the extension, right? Notice how it's F equals minus kx. That kx is a force too, because force equals force. Minus kx, that kx is a force too. The reason why it's negative is because it acts in the opposite direction of the force which induced it. That's why it's called a restoration force, right? Whenever you see a negative sign in front of an expression in physics, always think restoration. When you go into A2, I assume all of you are doing A2 physics. When you go into A2, you will see two more examples of this. The gravitational equation, which is F equals minus big G m1 m2 over r squared, negative sign. This is key for the universe because it literally means that everything in the universe actually wants to get back together again. Okay? Gravity always acts to restore things to to the state which they were originally at, right? If you think about the whole Big Bang thing, Big Bang theory, and how at some epoch, at the very beginning of time, there was a huge explosion and everything just blew outwards, right? Gravity aims to bring everything back together again. That's why gravity is the restoration force of the universe, right? And even it makes sense because gravity acts to, bring things closer together. So it naturally makes sense that it's a restoration force, right? The other example is voltage equals, I'm going to write this very lazily, d okay, that's a very lazy way of me writing the induction equation. Okay, whenever you have a magnetic field, whenever you have a changing magnetic field, that phi stands for flux, magnetic flux, right? Whenever you have a magnetic field or magnetic flux changing over time, you get a voltage induced in something. The voltage is induced in order to create its own magnetic field so that it can oppose the change which caused it. It can act in a way to suppress the reason why it was created. Okay? You're going to see this in A2 as well. Anyway, I've multiplied both sides by dx over dt in order to get my expression into something that looks a little bit like power. What do you suppose we do next? We don't integrate yet. We need to do a bit of cleaning up, okay? We need to do a little bit of cleaning up. Now, the left side is easy. Why? Because you've got dx and dx there, and they cancel. So at the end, you've just got energy over time, which is straight up power, okay? That looks easy. You just integrate that, and you get potential energy by itself, right? What about here, though? Here's a little bit trickier. How do we clean up the right side? Does anybody know? Or can anybody figure out? You barely spoken all.
I'm not sure. MD over dt.
Sorry?
Would it be MD over dt?
Do I?
Would it be MD over dt?
MD over dt. No. What we essentially aim to do, so if I have a look at this for a moment, we know that dx over dt is v, right? So we know that dx over dt is equal to v. What we essentially want to do in this case is that we want to do a little bit of, I don't like saying tricks because mathematics, there are no tricks in maths. is either it works or it doesn't work, right? But I'm going to call it trick. We need to do a little bit of a trick here where we express, if I recall, we express a dx by dt here as v. And we know that this dx over dt also equals v. Can you imagine me bringing out a dx by dt from this part, right? So let me highlight this part in green. Can you imagine bringing out a dx by dt there? From there, rather. Yeah. Because remember what I wrote some boards ago, right? That v equal, that you can treat this operator as if it was a variable. You can multiply it, you can square it, you can multiply it, la la la, right? I can also factorize it out. I can also factorize this operator out. So let me factorize one part of it out. So I've got m, then I've got d over dt right there, and I've essentially brought out a dx by dt, and I've got another dx by dt right there. Yep.
Wouldn't it just be d over t if you pulled it out?
I know, that's what, d over t? No, because that dt squared is actually dt. Yeah, it's all of it squared. It's just that we don't in maths we don't write bracket dt bracket squared. So what is dx by dt again? V, right? Essentially, I've got v multiplied by v, which is v squared. Okay. So I need more space. So currently we have d potential energy over dt, okay, because these two dx's cancelled out, and that equaled m v squared, and I'm just going to write dt there. Now don't be worried the fact that we don't have a half there. Doesn't really matter right now. Okay, the half is literally just, it's a constant. If you want to put it back there, you can put it back there if you want to. But we can clearly see that mv is essentially what? Kinetic energy. So when we integrate, we basically get rid, when we integrate with respect to time, we basically get rid of this time constraint. Now, what I should have done is that I should have swapped these around, because when you integrate, what do you get when you integrate indefinitely? When you have an indefinite integral, what must you always write? Constant of integration, right? So I'm actually going to swap these around and write ke there over dt. What am I doing? Equals minus dpe over dt. I'm going to integrate them once with respect to time, and I'm going to get ke equals minus pe plus c. When I rearrange and have c just on the right side, I just have ke plus pe equals constant. And that, my friends, is the equation, or the expression, or the statement which tells us that energy is conserved. The total energy in a system, whether this system is the classroom, well, it can't be the classroom because the window's open, but let's assume a perfect box, or the universe as a whole. The universe as a whole is a system. The total energy in the universe is unchanged, okay? That remains constant. However, what you can do is transfer between kinetic energy and potential energy, because those don't have to be constant, okay? Now, the reason why I gave you that exercise to do, because I found it interesting, and because it involved a whole load of expressions which you may have written down without thinking of, but it really gave you pause for thought, right? When you think about work done, how does work done even come about? Work done comes from a force. What do you do when you exert a force on something? You do useful work on it, okay? You build up energy in it. What exactly is potential energy? Is it just moving an object up, or is it actually just doing work on an object and building it up and you know, transferring energy from yourself into the object, okay? That is why, and also to build up your math as well, because math is important.